All right, so viscosity in a fluid is the friction in a fluid. So for instance, what that means is, let's say if you want to pump honey, honey will have greater viscosity will have greater friction than water. And so it's much harder to pump honey than water. Okay, so viscosity is friction in a fluid. And as you know, what viscosity does is, what friction does is it converts kinetic energy to heat. So when you brake your car, for instance, the kinetic energy of the car is converted to heat in the tires, in the brake pads, and all that kind of stuff. Okay, so just like that, viscosity causes part of the kinetic energy of a fluid to be converted to heat, which is internal energy. Okay. So now everything we talk about will be applicable to an ideal fluid. And so what is an ideal fluid? Ideal fluid doesn't have viscosity, meaning it's frictionless. So, well, even water has friction. Okay, so, but we'll be considering fluids where the friction is negligible. And then flow is steady, meaning, so here's a fluid that's flowing. So you can imagine a river, or you can even imagine a breeze blowing. And what we're going to say will be applicable to steady flow, meaning if you go to a location in the fluid and measure the velocity, that velocity will be constant. It won't change much over time. Okay, so the flow is steady. The pressure, if you measure the pressure there, the pressure will be steady. Okay, it doesn't change with time. Okay, and then the fluid is incompressible. So water is pretty much incompressible. So at least for the pressures, pressure changes we encounter. So the volume of the water doesn't change. Okay, and the last requirement is flow is irrotational. Okay, so see, what that means is the fluid doesn't have any eddies. So if the fluid has eddies, if you put a little fan-shaped paddle, the paddle would rotate in an eddy. Okay, so this fluid is irrotational. So you can put a fan anywhere here and it would not rotate. Okay, so this is a rotational flow and this is irrotational flow. So everything we say pretty much will apply to fluids like this. Okay, so again, the four conditions are: it's non-viscous, the flow is steady, it's incompressible, and we'll still apply it to air moving and stuff like that, even though air is incompressible. And so what we'll be looking at is situations where the pressure doesn't change too much and the volume doesn't change a whole lot. And the flow is irrotational. So what we say won't apply to fluids flow like this, but it will apply to fluid flows like this. Okay. And there's two things we want to learn. We'll look at. And the first thing is, so let's look at this pipe that has a different cross section. Okay, so the pipe is getting wider here. Okay, now it stands to reason, if you think about this, if there are no leaks in the pipe, whatever fluid is flowing in here has to flow out there. So the flow rate here at this location has to equal the flow rate at that location. And that's what's stated here. Okay. So the volume flow rate, area of cross section at this point times the velocity is equal to area of cross section times the velocity. Now when the pipe gets wider, the fluid flows slower. Okay. So when A2 is bigger than A1, V2 will be smaller than V1. Okay. So the wider the pipe, the slower the fluid flows. Okay, so that's the equation of continuity. And the second equation we'll study is Bernoulli's equation. Okay, Mr. Bernoulli studied fluids in motion. Okay, and so let's look at this example. So here is a pipe its cross section is changing and its elevation is changing. Okay. So we saw that how the velocity changes. That's given by the equation of continuity. Fluid flowing in here has to flow out of there. Okay. So if 100 gallons a second flow in here, 100 gallons a second have to move out here. Okay. So the velocity is pretty much determined by the cross section. Okay. Now, as the fluid rises, its potential energy also increases. Okay. So Bernoulli studied all of that, and he gave us an equation. We'll see this. Okay, so actually maybe let's look at this application first, this simulation first. Okay, can you guys see the simulation? Can all right, so you guys can see this. Okay, so now we'll illustrate some of the properties of fluid flow. So here is a fluid flowing, and if you constrict it, you see that near the constriction, the fluid has to flow faster. So for instance, I can measure the speed. The speed of the fluid here is 1.6 meters per second, and there it's 4.9 meters per second. Okay, so the fluid is moving much faster there. Okay, and that's just to ensure that if 10 gallons a second are flowing here at this location, 10 gallons a second have to move here. Okay. So let's make it slightly like this. Okay. Now, again, the speed there is that, and the speed there is that. Okay. Now let's measure the pressure. What the important thing is, what you learn is, the faster a fluid is moving, the lower the pressure. Okay, so again, here the pressure is 120 kilopascals, and here the pressure is 101 kilopascals. Okay. Now let me, okay. Now let me show you one other thing. So the pressure now here is 120 kilopascals, and here is also 120 kilopascals. So this is an ideal fluid, meaning there is no friction in this fluid. There's no viscosity. For a real fluid, you would have to measure a pressure. You would have to maintain a pressure difference to make the fluid flow. So see, there is 122. Oops. There the pressure is 122 as well. Okay. So, but for a non-ideal fluid, to maintain this fluid flow, you'd have to measure, you would have to maintain a pressure difference. So this is an ideal fluid. But anyway, okay, so you saw that, so again, let me emphasize this again. So the pressure here is 120 kilopascals. Here it's 105 kilopascals. The faster fluid, the lower the pressure. Okay. The fluid. Let's raise this thing. We'll raise this pipe. Okay. right. So now let's measure the pressure here. It's 121 kilopascals and it's 114 kilopascals. Okay, so you see this, the fluid velocity changes with cross section, the pressure changes with elevation, the pressure changes with velocity, and all that kind of stuff. All right, Mr. Bernoulli studied all of this, and here's the relationship he came up with. Okay, so what Mr. Bernoulli found was the pressure at any location plus the kinetic energy per unit volume at any location plus the potential energy per unit volume at any location. The sum of those three terms remains constant. The sum of those three terms is the same at every location in the fluid. And this is Bernoulli's equation. Okay. And again, this is valid for non-turbulent ideal fluids, non-turbulent irrotational flows. Okay, so this is Bernoulli's equation. It tells you that the sum of those three terms are the same everywhere. All right, so again, here are the two equations that we're interested in for fluids flowing. The equation of continuity that tells you how much the velocity of a fluid at different locations, and Bernoulli's equation, which states the sum of these three terms is constant. Pressure plus kinetic energy per unit volume plus potential energy per unit volume. The sum of these three terms remains constant. Okay. Now we'll just look at some fun applications. Okay. So for instance, so by the way, going back to this equation. So again, the sum of these three terms is a constant. So let's say we will not vary this. Now this equation tells you if the velocity of the fluid increases, when this term increases, that term has to decrease, this remaining constant. So whenever this increases, that has to decrease to maintain the sum of the three to be constant. Okay, so here's an application. So you all probably have experienced this on the highway. So when you pass a truck or whatever, so now this air has to go in a smaller space, so it's going faster. This air is traveling faster, so the pressure here is decreased. The pressure there is higher, so these two vehicles get pushed toward each other. Okay, and sometimes that can be disconcerting, especially if two truckers are passing each other, or if you're pulling a trailer or something like that. So you'll feel a force of attraction towards the truck, whether you want it or not. Okay, so you guys have all flown on a plane, and so how does the plane stay afloat in air? Okay, so when the plane is flying this way, the air is flowing in this direction, and the way the wing is shaped, there is the airfoil. See, this has a curvature, so the air has to flow over a greater distance there. It's flowing faster. The pressure there is lower than the pressure here, and that provides most of the lift. So curvature of the wing surface causes pressure above the wing to be lower than below the wing, giving it a lift. Okay, so here's a computer simulation. Here's a computer simulation, and you can see because of the curvature, the air above is flowing much faster. This column of air is over there, and this column of air is here. So because pressure differences, because of this speed difference, accounts for most of the lift of the airplane. Okay. Now, turbulence and lift. So if you're aware of planes flying and stuff like that, if the angle of attack is too large, you will have a transition from laminar flow to turbulent flow, and the plane can stall. Okay, so if the nose point of the plane points too high up, the plane will stall and you lose lift and you'll fall off the sky. Okay. So turbulence, so here's turbulence. Turbulence increases drag and reduces lift. Okay. Now, you guys might, if you play tennis, you know that people like to put topspin, and here's the reason why you put topspin. So here's this ball, tennis ball traveling in that direction. The air is traveling in this direction. And if you put a topspin on the ball, if it's spinning like this, what the topspin does is it grabs this air and that makes that air flow in this direction. So the airflow around a spinning ball is like this. And this topspin, so this air has to travel a greater distance. It's traveling faster, the pressure is lower, and so the pressure here is higher. And so hence the ball feels a force, downward force. So here's a top spin ball that's hit in that direction. And because of the spin, it's feeling of experiencing a force in this direction. And so that ball will land inside the court. Okay. So if you hit a ball without any top spin, a straight ball, that will fly outside the baseline. So that's why you put a top spin. It gives you more room for error. Okay. Here's a great YouTube video about the topspin that I suggest that you guys go see. So that illustrates the Magnus. This is called the Magnus effect. Okay. Here's another application of pressure and velocity. Okay, so here's an atomizer. You guys have used bottles, sprayers all the time. And what you do is, if you blow air, the velocity of air increases here. That decreases the pressure, and that decreases the pressure less than the atmospheric pressure. And the atmospheric pressure will push the fluid up into the stream, and then you get a stream of the fluid. So that's how sprayers work. Okay. Again, when you blow this air across, the pressure decreases here. Pressure here is higher, which pushes up the fluid there. Okay, we'll briefly talk about viscosity. Okay. Viscosity, again, is friction in a fluid. So here's a fluid. And so think of two, so think of two light wooden surfaces, planks. Okay. So let's say you push this wooden plank, and then you get layers of fluid moving. Okay. So the force you have to keep applying, the force you have to apply because of friction, you have to apply force against the friction force to keep this plank moving at a steady velocity is given by that. That force is the viscosity of the fluid. The viscosity is the friction in the fluid. Velocity is V is the velocity of the plank, and A is the area of cross section of the plank. Okay. Divided by the length, how far apart they are. Okay, so that is the thickness of the fluid. Okay. Anyway, here's where viscosity comes into play. So here's a pipe, and you want a certain flow rate of the liquid. So this could be an oil and being pumped. And for this flow rate, Q, the pressure difference you have to maintain for a given flow rate, the pressure difference you have to maintain is given by this expression. P2 minus P1, 8 over viscosity divided by the length. Okay, so greater the viscosity, greater the pressure difference you have to maintain for a given flow rate. So, for instance, oil has a much higher pressure viscosity than water. So, to pump oil, you have to work harder. The pressure difference has to be higher. And even for oil, for instance, oil at a higher temperature has less viscosity than colder oil. So when they pump oil through the Alaska pipeline, they warm the pipes warming the oil, so the viscosity decreases, so they spend less energy pumping that oil. Okay. All right, that finishes these slides, and I will stop the recording now, and